Hello, class. This is the last thing you're going to learn right before the midterm. It's called logistics. And it is a growth model, and it usually shows growth of some type of population, whether it be like bears or bunnies or something like that. Bunnies. So, anyway, this is what it looks like, and here's some of the players. It's a formula, right, model, that says the derivative with respect to p over the derivative with respect to time is equal to kp times the quantity m minus p. Let me tell you what some of these players mean. P is the number of species present. Okay? M is its carrying capacity, means how many of them can exist. All right? And usually a logistics graph looks something like this. Okay? It'll go here and it would kind of like go like this and kind of level off at some spot. And if we're talking about population, that's time over population. A lot of times it's looked at just the positive area. Okay, but that's in a logistics graph. If I switch this around and solve for p by separation of variables, you know separation of variables, like put the dt on one side, take the integral of both. You've done that before. All right, then I get this. And let's talk about these players. A is a constant determined by the initial condition. Just some constant, all right? M is the carrying capacity. K is the growth constant, all right? In science, they solve for the growth constant, okay? In math, we could solve for the growth constant. If the growth constant is negative, it's actually a decreasing population, and that's how they determine whether things are becoming extinct or not. So, one of the things that's always growing fastest at half carrying capacity. So if I had 100 bunnies, it's always growing the fastest at 50. That's it. And this actually was a question on an AP test about 10 years ago, I guess. Limit as t approaches infinity, as it goes forever, you know, and this is m, carrying capacity, because that's where it's approaching. So that's what it is. Let's do a couple problems here. The growth rate of a population P of bears in a newly established wildlife preserve is modeled by this equation. So this is given. This guy is given equation, all right? That guy's given. What is the carrying capacity for bears in this wildlife preserve? Well, holy cow. I can go and just check it out. It's 100. Done. That's what it is. All right? What is the bear population when the population is growing the fastest? Well, all we have to do is know that the bear population, when it's growing the fastest, what is the population? It's always half the capacity when it's growing the fastest. So all these crazy questions in a crazy equation, I'm just using half capacity, half at the capacity is when it's growing the fastest. 100 is the total. Yes, people, it's this easy. Then it says, what is the rate of change of the population when it's growing the fastest? So all you got to do is put 50 into that equation. So it would be 0.008 times 50 times 100 minus 50. And I think you get about 20 bears per year. All right, you get about 20 bears per year is the rate of the change of the population. All right, that's all you do is you plug that guy in. So far, so good. Russ, you good?
Good.
Russ is good. Okay. So next. I don't even know what I'm looking at, to be quite honest with you. But here's a population of bunnies. I found it somewhere. And let me make it. Let me. There's like different stuff here. Because it's bunnies, we gotta love it. We gotta love the bunnies. So I do sing, Katie. I do sing crazy bunny songs because I'm obsessed. And you haven't really got me any help. So I'm gonna stay what I stay. All right. So that's our equation for this population of bunnies. And now, part 1 says, identify K and the carrying capacity. Well, K looks like 0.07, because this is the K, Okay, you might say negative 0.07. I don't think so. I think it's just whatever's in front of t. All right, let me go back to my original equation. Yes, mkt, the constant determined, blah, 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 growth constant. It's whatever's in front of t. All right, so that's what we're going to say. We're going to say it's that. All right. Then it says the carrying capacity. Well, that's easy. Carrying capacity is 1,000. So M equals 1,000. And this is K, because it's always KT. I know it said MKT, but I'm not going to solve for it. All right? Estimate P of 0 and what it means in the context of the problem. So P of 0, I'm going to use a calculator. Okay? I'm going to use a calculator and do 100 equals 1,000. I'm sorry, not 100. 1,000 times 1 plus e to the 4.8 power. That's at time 0. And this is approximately 8 bunnies. And that stands for the initial population. That's what it means. So I just found out how many bunnies we started with. Fantastic. Damn, 8 bunnies to 1,000. God. All right. Anyway, something else we have here, and I have this problem as an example. It says, find y of t if y of 0 equals 3. I don't know why this is all highlighted, so we're going to take rid of this highlight. But let's find out what I do. Okay? I do this for you. So this is going to be, I'm going to take dy, and I'm going to move this guy over here so it flips. All right? So I'm going to flip y and 5 and put it on the dy side. I'm going to take dt and put it on this side and then integrate both sides. This is called separation of variables. We've done this before. So now I have the integral of 5 over y, which is just 5 ln of y. And then on this side, over here, when I take the integral of this, I get t minus t squared over 24. Makes sense, just taking integrals. And now I need to find y of t. So now I'm going to e both sides. This is new. This is a new thing. Here, hold on. This is where it got ugly. And I know Russ doesn't like it. So give me a second. Okay. All right. So one of the things I did was I put 5 I put onto the power. And now I'm going to e both sides. Here, I'll do this one in... Oh, I erased too much. I hate myself. All right. Here we go. We're better now. And I'm going to e both sides. Why do I do that? To get rid of this. All right? That's why I do it. So I get y to the 5th is equal to... Now I take e to the t, like that stuff. And I'm going to get... e to the t minus t squared over 24. But now, when you have a constant and you raised it to e, because we had a constant plus c here, e to the c, they just say is c. So this is what happens when you e both sides after an integral, all the time. And now, just to find y, I take the square 5th root, if you will, of this ugly thing. All right? I know y of 0 equals 3, so what I'll do is I'll solve it for c to equal 3 to the 5th, okay? So when y is 0, check it out. 0, 0, 0, this is 3, so I have to solve this problem, all right? And that's what I get, 3 to the 5th. That's it. This is not even homework. I don't want you to look at this. Okay, but I solved it for y equal. Remember, if I put in 0 for all these t's, I get c times 1 is e to the 1 power. So I actually have, and this is for the people that didn't see it, I have this. Okay, but now I know y is 0, which I put in. This is 3 is equal to this. So that's how I got c to be 3 to the 5th power. All right, that's logistics, folks. You'll have one like that on the midterm. We might do one in class if we have time on Monday. All right? We probably will. All right, take it easy.